When you shine X-rays onto a piece of glass, it bends away from the normal. And that's weird because when you shine normal visible light on the piece of glass, it bends towards the normal. And the reason for all this bending, which we call refraction, is that we usually say that light, when it travels from vacuum into glass, it slows down. And because it slows down, it bends towards the normal. And now you can see why this is weird. If it bends away from the normal, it means light will speed up. So does that mean that X-rays, they speed up when they go from vacuum into the glass? Would that mean that X-rays travel faster than the speed of light in vacuum, in glass? No, they don't. And this brings me to the biggest lie in optics. This statement that we say that light slows down when it goes from vacuum into glass is a big lie. Turns out light, whether it's visible light, X-rays, or any electromagnetic wave, it always travels at the speed of light c, the speed of light in vacuum, in all materials. It never slows down, or for that matter, speeds up. But then how does refraction happen? How does optics work? Well, it turns out that even though the speed of light always stays the same, light can either take more time to travel through a material, like in this case, or it can take less time to travel through a material, like in this case. And I'm sure this sounds a little confusing, and I was confused as well. And so I went through Feynman lectures for the past few days, and after going through all the math that he goes through in intricate details, my mind was blown, because by connecting the ideas of oscillations and waves and electric fields, all of the high school physics, I think we can develop a pretty solid intuition behind what's really happening when light enters from one medium into another. And that's really what I want to talk about, and then eventually clarify what really happens with the X-rays. So if you're as excited as I am, let's begin. Let's first start with why I said that light always travels at the same speed, the speed of light in vacuum. See, the common explanation for why light slows down when it goes from vacuum to glass is like using an analogy. It's like, hey, a car going through mud, right? It slows down. Something similar is happening over here. The problem is light is not an everyday object like car. So you can't just use that analogy. In order to see from the perspective of light, we can't see it at a macro level. We have to dig a little deeper, not at the atomic level. We have to go subatomic level. If we go inside an atom, we see that atom is mostly an empty space. All the mass of the atom is concentrated into the tiny nucleus at the center. And to give you a perspective of how tiny the nucleus is, imagine the atom is as big as a football stadium, okay? Do you know how big the nucleus would be? All the mass of that stadium would be concentrated into the nucleus at the center, and it would be as big as a grain of sand. The rest of the atom would be completely empty. There will be electrons zipping around, but even the electrons are like tiny dots. So from a microscopic perspective, an atom is just empty space. More than 99.99999% of the atom is empty. And therefore, from light's perspective, it's always vacuum. Whether you're talking about glass or you're talking about water or any other material, light will always be traveling in vacuum, and therefore the speed of light will never change because it's always traveling in vacuum. Speed of light stays the same. And this also helps debunk this popular idea that states that, hey, you know what, light doesn't slow down, but it bumps around, and that's why it gets delayed. Now you can see there's nothing to bump around, right? Like it's mostly empty space. And by the way, if light were to bump around like this, then there is no reason why light has to travel in a specific direction. It would have traveled in all the possible directions. So clearly this model is wrong. So what is really going on as light travels through this empty space? Well, for that, we need to remember that light is an electromagnetic wave which consists of electric and magnetic fields. And we need to see how it affects the electrons over here. So let's do that. So here's light from a flashlight. I've drawn the electric field vectors over here, and I'm ignoring magnetic field vectors because they're not going to have any significant impact when it comes to refraction. So we'll ignore them completely for this video. All right, so now we have light, we have electromagnetic waves traveling at the speed of light. Let's imagine it's traveling to the right. What happens when I introduce a piece of glass? Now, it'll be a little harder to think about what happens if I have a thick piece of glass. So the way we'll do this, the way we'll deal with this is we'll first start by thinking about an extremely thin piece of glass. What is the effect of that? And then we'll imagine that our entire glass plate is made up of a lot of such thin materials, and we'll have a solid intuition for what really happens when it goes through the glass. All right, so what happens when it goes through a thin piece of glass? Well, this piece of glass has a lot of electrons inside of it. Electrons are charged particles, and when electromagnetic waves go through these electrons, they will put a force on these electrons. So let me just zoom in a little bit. And so you can see as the electromagnetic wave travels through this electron, you can see it starts pushing up and down on that electron. And as a result of that, we'll find that this electron will keep going up and down like this. It will keep oscillating. So because of that, what happens? What happens to my electromagnetic wave because of the electron oscillating? A part of me says that maybe the electromagnetic wave gets absorbed and maybe something happens as of now. But that's not the most rigorous way to deal with this, because when you're at the end of the day, we're dealing with electric fields over here, right? When we're dealing with electric fields, we never say electric fields get absorbed. That's not how we deal with electric fields. We'll deal with it by using the superposition principle, which is a fancy way of saying that the original electromagnetic wave just continues to go through at the speed of light as if nothing has happened. But now these oscillating electrons are oscillating charges. They will generate another electromagnetic wave. You might remember that oscillating charges are the source of electromagnetic waves. That's how electromagnetic waves get created, at least in the classical physics, right? So all these oscillating electrons will generate an electromagnetic wave, which I'm going to show as a blue wave over here. This will have the same frequency as the original wave because the electrons are oscillating at the same frequency as the original wave. And they will also be traveling at the speed of light because it's in vacuum. And when you combine these two waves interfere with each other to give you a combined wave, and that's the wave that is traveling through the piece of glass. This wave that is traveling in the piece of glass is the combined wave, and that wave is also traveling at the speed of light. So the speed has not changed because two waves traveling at the speed of light will combine to give you a resulting wave that also travels at the speed of light. But once we look at this carefully as to how these two waves combine, we'll get the secret. We'll understand the secret of why light gets delayed over here. All right, now before we can answer as to what the resulting wave looks like, we need to look at two things. One is how big this new wave created by the electrons will be. How big will that be? Because the resulting wave will depend on that. And the second thing will matter is how is it in relationship with the original wave? Would its peaks and valleys be lined up as it is? Or will it be somewhat like this? Or basically, how will it be, right? These are the two things that we need to think about. Well, the first one, how big these waves will be, well, that purely depends upon the material, like how many electrons are there, how many of them are oscillating and all of that. We'll not worry too much about it. We'll just assume it's going to create a smaller wave. All right. But the second one, that's the more important one for us. Like, how will this be? And I'm going to zoom in a little bit. What will be the relationship of this blue wave, the wave created by the electrons, with respect to the original yellow waves? Will it be in line like this? Will it be like, peaks and valleys will line up? Will they not line up? Will it be somewhat like this? What's going to happen? How do we figure this out is the question you might have. Mahesh, how do I know, right? Well, we can make one simple assumption, and using that assumption, we can get some intuition behind how this would be. So the assumption we're going to make is that we're going to assume that light, the glass piece does not absorb any light. We'll assume that the energy of the light stays the same as it travels through glass, which is a pretty reasonable approximation. Just based on that, we can pretty much guess how the blue wave should be, like the relationship in phase, we say, with respect to the yellow wave. And I want you to pause the video and think about it. Do you think, under this assumption, the blue wave will line up, or they will line up in such a way that the peaks and the valleys line up, or it'll be something in between? I want you to pause the video and think about it. Just by using energy conservation, you can answer this question. Okay, hopefully you've tried. So let's look at it one by one. So imagine the peaks and valleys exactly lined up. What would the resulting wave look like? Well, everywhere the electric fields would add up. So the peaks would become bigger, the valleys would become bigger. So the whole wave would become bigger, and the resulting wave would look somewhat like this. You will get a bigger version of the original wave. And that violates energy conservation because now I have more energy out of nowhere. This is energy creation. So I know for sure this cannot happen. Okay, what else? Let's see what happens if we line up the peaks with the valleys. If you line up the peaks with the valleys, everywhere there'll be destruction. right? All the electric fields will tend to cancel each other out. Now they won't perfectly cancel out and become zero because the blue wave is smaller than the yellow wave, but the resulting overall wave would be smaller than the yellow wave. So the resulting wave would look somewhat like this, smaller than the original wave. And that also doesn't work for us because here energy is destroyed and we assume that there is 100% energy transfer. There is no energy loss, which means we know this also cannot happen. So just by using energy conservation, I know that my electron wave cannot perfectly line up with the peaks and valleys. I also know that the peaks and the valleys cannot line up as well, giving you a complete destruction, which means it has to be somewhere in between like this. It's going to be somewhere in between, and I don't know exactly where, and that doesn't matter exactly where it'll be, but somewhere in between like this, such that there will be some destruction over here, there's going to be some construction over here, and in such a way that the resulting wave will have the same height, it'll have the same energy as before. This is how the electron wave will line up, and I find that pretty mind-blowing that just by using energy conservation, we can guess this. And turns out that when you look at the equations, that's exactly what you get. And that's one of the reasons my mind gets blown, because we can use high school physics principles to deal with such incredibly complex stuff. Anyways, now the question is, what would the resulting wave look like? I know it's going to have the same height. It's going to be in such a way that it has the same height. But interestingly, let's look at where the peaks of the new wave would be. So when this interferes, you can see that this part will undergo some destruction. Here there will be some construction. So the new peak will no longer be over here. It'll be somewhere in between this peak and this peak. One way to see that is that you can kind of see that this one is trying to sort of pull this peak back. This one is trying to pull this peak forward a little bit. So eventually the new peak will be somewhere in between. And if I draw that, this is what it would look like. Let me just zoom out a little bit. All right, there we go. This is the resulting electromagnetic wave that is traveling through glass. It's traveling at the speed of light, same speed, c. It has the same height, but you can see the peak is slightly behind. And this is the reason why the light gets delayed. Let me show you, and this is the interesting part. Here it comes. So if I put this on top of that, you can see where I'm going with this. All right, so here you go. All right, so this, concentrate on the yellow one now. I'm gonna get rid of the blue one so we can concentrate on the yellow one. Okay, so without the glass piece, this is what the electromagnetic wave would have looked like. But the moment I put this glass piece, it's gonna generate the blue wave, and that blue wave is going to pull back on the electromagnetic. Because of the blue wave, the electromagnetic wave gets pulled back. Can you see that? Boom, gets pulled back. Can you see that? Pulled back. And because of this pull back, the wave has to travel more distance. And this is pulled back due to one piece of glass. There are multiple pieces of glass, each one pulls back. And here's the animation. Let me show you the animation. So below we'll see what happens without the glass plate, and above we'll see what happens when I introduce the glass plate, and we'll be able to see the difference. So here we go. We have electromagnetic waves coming in, and now I'm going to introduce the glass plate somewhere here and see what's going to happen because of that. All right, here we go. Now I have not shown the interference yet. Now see what happens because of the electron wave that it produces. It's going to get pulled back. So see what happens. Here we go. Here we go. Boom. Did you see that? Did you see that? Look at that. And boom. That is the effect of the electron wave interfering with this wave. And as a result, notice the resulting wave has always been traveling at the speed of light. That did not change, but it got pulled back, and that was the result. It started, it started lagging behind what it would have been without the glass plate. All right. And now I'll consider more and more glass plate, and as a result, you can see it'll keep on continuing to do that. Boom, pulls back, boom, pulls back, boom, pulls back. And that's why it takes more time to travel that distance compared to the original one. Isn't this amazing? I find this pretty amazing. And here's another thing, all right? I'm deliberately choosing not to look into the glass plate because this is as much as we can do without any math, okay? But you can kind of sort of see that if the light is being pulled back due inside those thin glass plates, the wavelength must shrink over there. And so from this, I can pretty much say that the wavelength inside the glass should reduce. And we know from optics, that's what happens. But now we have a much better intuition behind why that happens. Light always travels at the speed of light, but it gets pulled back, and so it has to travel, it takes longer to traverse through that path. And that's why we say it slows down. Does that make sense now? But what happens when it comes to X-rays? So let's go back to our drawing board, And let's go back to that wave interference. And at this point, you should have actually asked me one question. I mean, you probably did, but I wouldn't know anyways. But see, when we looked at energy conservation and we said that, hey, the peaks and the valleys and valleys cannot line up because energy would be created. And the peaks and valleys can't line up because the energy would be destroyed. And therefore, it has to be somewhere in between. And that's how the wave got pulled back, giving you this delay. But there's another way in which the energy can be conserved. Instead of the blue wave being behind the peak of the yellow wave, the blue wave could have been ahead the peak of the yellow wave. I can also set it up in such a way that the two waves interfere to give me a wave that has the same height. If this happens, and that can totally happen, based on the energy conservation logic, this can totally happen. And if this happens, then we'll find that the resulting wave will have its peak, which is slightly ahead of the original wave. And now if we bring this over here, then you can see that the wave gets pushed forward because of the interference. You see that? Boom, it gets pushed forward. And again, I can show you an animation of that, and that's the result why you can apparently travel faster through glass as well. So let me go back to the animation, and let's imagine in second case where the wave gets pushed forward. If this was what would have happened, then let's see. I'm gonna introduce a glass plate now. All right, here we go. Now due to the wave interference, it's gonna push that thing forward. So keep an eye on this and you will see it gets pushed forward. Boom. Due to the wave interference, it pushed forward, and that can continue to happen. I keep more and more glass, boom, boom, boom. Because of this, you can apparently travel faster in glass than, you can cover that distance faster than you would have covered that distance without the glass. So in some sense, it feels like you're going faster through it, even though you're not breaking the speed of light. You're constantly going at the speed of light. And that's how you can have two things happening. And you can now probably guess that when it comes to visible light, you get the phase lag. And when it comes to X-rays, you get the phase lead. In other words, it pushes forward. And so we now have explained intuitively, to some idea, some degree, how you can travel faster apparently or slower without breaking the speed of, without ever changing the speed of light. But the last question would be, why is it that in the visible light, you end up getting pulled back? And why is it in the X-rays, you end up getting pushed forward? And this now is the last piece of the puzzle. And full disclosure, I don't have complete intuition on it. At this point, Feynman's equations became too heavy for me, but here's my perspective, here's my take. We now need to think about forced oscillations, and here's my logic, all right? Electrons inside that piece of glass, they have a natural frequency at which they would like to oscillate. All right, this is what we call the natural frequency. It's kind of, imagine that if I could tap that electron, it would oscillate with some frequency. It's natural frequency, and that happens to be somewhere in the region of ultraviolet light. That frequency corresponds to the ultraviolet frequency in the electromagnetic spectrum. That just happens to be a fact when it comes to glass. All right. Now, what happens when you shine visible light on such electrons? Visible light has a much lower frequency compared to the frequency at which electrons would naturally tend to oscillate, right? And so as a result of that, the electron, so when you force the electron to oscillate at a lower frequency, the electrons are like, cool, I can easily oscillate like that, right? Because electrons can naturally oscillate much faster. And so they have no problem oscillating at the frequency of the visible light. So they would be pretty much oscillating in phase with the visible light, which means the wave that electron would create should also be in phase with the visible light. So if we go back to that electron wave, it should look like this, right? Because the electron is oscillating in phase. And that was confusing for me. This was the part that confused me. But then I realized this electron wave is not a wave created by one single electron. It is a wave that is created by all the electrons. The wave created by a single electron will be minuscule, right? You have to add up all the waves created by all the electrons, and that is what the blue wave is. And that's where the math gets heavy, because you have to do an integral. So the wave created by this electron would be perfectly in phase with the yellow one, right? But what about the wave created by this one at some point over here? Let's consider that over here. Now, because this distance is larger, can you somehow imagine that if you consider this peak from this electron, it takes, by the time it reaches over here, because it's a slightly larger distance, this electron wave, both of these electron waves would have traveled a little forward. Does that make sense? And so when that finally arrives over here, that peak of this electron would be slightly behind this peak created by this electron. And when these two interfere, we will get the resulting peak of the resulting electron wave slightly behind. Same would be the effect of addition of the waves from this electron. Similarly, if you consider now the waves created by this electron and this electron, which is even farther away, by the time this peak of this electron reaches over there, and I know you might be losing me at this point, but again, at that point, again, if I consider both these waves, they would have gone forward, and now their peaks would arrive at this point, and when that interferes with the blue wave gets pulled back a little bit more. Long story short, here's the way to think about it. Long story short is that this electron wave would be in phase, but if you consider the waves created by the other electrons, they would be lagging behind, and when you interfere all of them, that's how it gets pulled back. Don't know if that made sense, but I have some intuition as it's a hand-wavy explanation. And as a result, the combined wave ends up being slightly behind, giving you that delay. And that's why the visible light eventually ends up apparently slowing down. But what happens when it comes to X-rays? All right. Well, X-rays have a higher frequency than ultraviolet, which means if this electromagnetic wave was X-ray, then the electromagnetic wave would be forcing the electron to oscillate at a frequency much higher than its natural frequency. And the electron says, I can't keep up with you. So now, if this is the X-ray, it's oscillating much faster, and the electron has no choice but to oscillate with that frequency, but it won't be able to catch up. What will happen when you consider oscillations, forced oscillations, is that it'll lag behind so much such that, when it goes up, it tries to go up, but when it's going down, it'll end up going up. So you'll end up having something like this. This is how it will be. So they'll be completely out of phase. When this is peaking, this will be giving you a valley, and when this is peaking, this will be giving you a valley. So now if you consider the wave created by this electron over here, that wave would look like this, perfectly out of sync with the original wave. But when you consider the wave created by all the other electrons, it'll have the same effect of pulling it back. This blue wave gets pulled back when you add up all the waves from the other electrons. And now look at it. Notice this very carefully. What happens when I pull the blue wave back from this position? I'll pull it back a little bit from this position. I'll pull it back, and you see the peak ends up lining up ahead of the original wave. And in some sense, that is the reason why when you shine light with a higher frequency than the natural frequency of the electrons, eventually the electron wave becomes ahead of the original wave, making sure the resulting wave gets pushed forward, making sure the distance gets traveled faster, giving you an apparent speed faster than light, speed of light in vacuum. And that's why when you shine X-rays, because the apparent speed is faster than light, it bends away from the normal. I had a lot of fun researching about this, definitely out of my comfort zone, trying to make something as complex as this. And I'm really curious to see, how do you like it? What are some places that you didn't make sense? Start a discussion, and I'll reply to all the comments. And a question for you is, based on this explanation, we can clearly understand how dispersion works. Like really rigorously understand beautifully how dispersion works. And I'm curious to see if you would be interested in knowing that. Bye.